All right, well, let's talk about function families. Our first family is linear functions. Now, you could write this as, you could say that I have f of x equals, mx plus b, and, this is where I can add sliders. So this could be one way we look at it, and what we know is we always have a straight line, and the b, you could say it's sliding this thing this way and that way, but actually it's just going up or down, right? That's the y-intercept. So if I want to move this around in terms of the parameters of the family, I can do that simply by doing this. But also notice that I could have, instead of saying mx plus b, said, well, this is my a times the x, and then this is that d that moves things up and down, and we add that, and I get rid of the m and the b, and so if I think of my two parameter family this way, is the a, you usually think of that as making something taller or shorter, but you see, well, if I'm sort of stuck here at this y-intercept and I take this point over, say x equals 1 right here, and I want to make it taller, what's it going to look like? It's going to look like this thing's rotating. So, as you change a, one way to think of it is you're rotating, but another way to think of it is, right, you're making it steeper and steeper because it's taller, right? So we can make it steeper, and if we change to a negative, then it goes down to the right, or we call that decreasing, so it's either increasing or decreasing. And then, of course, we can change the intercept by moving the d here, or what you're used to with b's in the mx plus b sort of thing. Okay. Now, the one line we can't get to, although that line's not a function anyway, is the vertical line. Whereas now, if instead we looked at this as an implicit, or what they call the general form, right? We could say ax plus by either equals c or plus c equals 0. So I'm going to say equals c, and add sliders. Now we're using this a because I already had a. But now, so let's turn this one off. Here, the thing is if I make either a or b 0, then we get certain things. So, right, if b is 0, so I come down here to 0, that's when you get the vertical line, when b is 0, and a, we can move it around, and it seems to be shifting things back and forth a bit. Well, why is that? Well, because you get this ax equals c, and so you have to get x at the spot that works out for a and c. Then if we let b be non-zero, but then we make a 0, then that's when we get a horizontal line, because really what we have is y equals a constant. Okay, because if b is non-zero but a is 0, you just have a constant times y equals c, so we divide. So this general form, the one thing it has over the function form is that, or what you tend to call the the slope-intercept form, but this function form, we cannot create a vertical line out of this because it's a function, and vertical lines are not functions. Here, this general implicit form, where I could really either think of x as a function of y or y as a function of x, in that implicit form that we tend to call the general form, then in that case I could actually give you a formula for a vertical line out of that. Okay, but that's our function family of linear functions, really just the a and the d going on there. Okay, now to move up from there, and this is to some extent where really the A, B, C, D thing just disappears, and that's because in a polynomial, we might have something like, let's go with maybe a fifth degree polynomial. So I have a5 times x to the fifth plus a 4x to the, try that again, to the fourth plus a 3x to the third plus a 2 x squared plus a 1 x to the first, and then plus a 0. And we'll add all those sliders in. I don't see anything here, and so what we might do is zoom out, see if we start to see it. Nope, but let's do some things like let's make this 0 and that 0 and that 0 and see if that helps us any find this thing. No, I don't see it, but that's interesting. I thought we'd see it somewhere. Alright, well, let's make this one 0, and well, that's really weird, because right now we've got a slope of, sorry about that. Look, didn't have it on. Okay, so we'll take a 2, and so we had a straight line, but now as I add an a2, all of a sudden this thing gets that familiar parabola shape, and now with the a3, when that's not 0, now we get this thing that kind of goes like this, different ways, but it has no humps, but I can make it so it has 2 humps, but never can I make it so it just has one, either a trough. So there it has one, but I didn't really, because you see I made a3 0. But as soon as a3 is not 0, it either doesn't have the trough, or I can, if I make it negative, you see I can get a trough and a peak. Okay, so I get sort of these 2 humps that way. Now let's add something with the fourth on there, and what we see is right in there. Now I have something with 2 peaks, 1 valley, or 1 trough. So 2 humps, 1 trough, and that's the 4th degree. And if I try adding the 5th, I don't know if I can get. It's pretty And I can start messing with these. Ooh, look at that. That's starting to look pretty strange. Ooh, there we go. Okay, so if I zoom in a little bit in here, what we see is there's a peak and there's a small peak. All right, so there are two peaks and two troughs. A small trough, again, a small trough. And what we're seeing is that we can actually characterize by the degree here what we might see. And so let me put a couple other functions in there. Let's put in, we'll use y equal x, and we'll do y equal x squared. Okay, and really these two are telling us a lot about the behavior of all the other polynomials. So y equal x is a polynomial, and y equal x squared is a polynomial. They just happen to have all their other coefficients 0, and the one coefficient they have that's non-zero is 1. But here's y equal x, and notice y equal x, odd degree, an odd function, and that odd function, in this case, what happens is it either, as this odd thing, it's either going to grow as you go to the right and diminish toward negative infinity as you go to the left. It's going to do either that, or if I toss a negative in front of it, then it does just the opposite because it flips it over the x-axis, and so it diminishes to negative infinity on the right and goes to positive infinity as I go out to the left, or it comes down from positive infinity as it moves to the right. Okay, so actually, so if you can remember what x does, y equal x does, then you sort of know what y equal x cubed, y equal x to the 5th, y equal x to the 7th, y equal x to the 9th, y equal x to the 11th. I'll stop on that now. But all those odd powered functions, and that also means the degree. Okay, so the degree, if the degree is odd, so the leading term here, that is, the leading term has the highest degree, and so in this case the leading term is x to the 5th. If that is odd, then what I know is at the ends, out here, at some point when x gets big enough, this polynomial, because its degree is 5, it will either head up here like this out to positive infinity. In this direction it will head to negative infinity, just like y equal x. It will either do that, or if this a is negative, so here see our a is a5 is positive, and so it's behaving just like y equal x. Now make it negative, and now at the two ends, going out toward the large x's or going out toward the negative numbers that are large in absolute value, it acts like y equal negative x. Now it's much steeper because the numbers are much bigger, but it's acting like y equal negative x. It's kind of doing this. It's got the squiggly stuff in the middle, but it's pretty much doing y equal negative x. And similarly, when we get rid of that if I can, there we go. When we do that, notice that looks a lot like y equal x squared. It's wiggly in the middle, but other than that, it looks like y equal x squared. And that has a is positive, and so it's opening up just like y equal positive x squared. But if I come down here and I put a negative on x squared, then it opens down, and it ends up looking like that. Let's see if I can do that. Well, I know I can do it. I just don't know how wiggly it'll be. So it looks, definitely like a thinner parabola. But you see, by going to negative 0.4, yeah, it's doing what negative x squared is doing. Okay, and or sorry, negative 1. I don't know about negative 0.4. It's negative 1 I went to. A little slow sometimes. But if we go back up here to the 0.9, 0.7 or whatever I was, then it's the positive x squared. And okay, so if if you're thinking about a polynomial family, and you're just kind of, the coefficients, as I add those, oh yeah, those will do all sorts of weird things in the middle here, and we'll talk about that momentarily. But all I really need to know is look at my leading coefficient. So here I made the a5 0, so my leading coefficient is the a4. So that's x to the fourth, an even number. So that acts like a parabola. And then a4 is positive, so it's going to open up. And so it's going to act just like y squared in that way. Now, what I don't know is the middle. And again, if I increase a5 just that, even that little bit, all of a sudden what we see is the center, again, very wiggly and strange, but the outside parts, they're pretty much acting like y equal x here, right? So that's heading off up that direction just like that is, and this one heading down toward negative infinity just like this one is. Okay, so if I know what y equal x looks like and y equal x squared looks like, and I know what the minus does on them, then all I have to do is look at my highest degree term and look at its coefficient, and I know basically what's going to happen on the outside part. Okay, so this one does do something like this. If I make this negative, it's going to switch this one heading down, this one heading up. So I come over here, I make it negative, and sure enough, that's what happened. Okay, now what about the middle? Okay, well let's think about this for a minute, and let's go back to a quadratic or a linear or something like that. Okay, so I would say we're pretty comfortable with get my face out of there. Okay, we're pretty comfortable with, I think, a parabola, does this. We've at times entered lots of data into graphs and all that, and I think people kind of go, yes, it's a parabola. Now, let's think about it for a minute, what has to happen here with the degree 2. If we've decided that when x is heading, well, and let's make this positive just so it looks that way. With this way, if when we head out for large x, this has to head up that way, and when we head out this way to the left, this has to head out that way. If we've decided that has to happen, then in the middle, what else could happen? And well, there are a few ways to look at this, but I could only have one lump in here. Now, you could say, well, actually, I could come down, go up again, come down, go up again. Okay, now we're going to see why that's not going to happen. Because we can tell you the most number of times it could possibly do that. And I can do that simply by taking a0 here, making it negative, and right, there's a 0, and there's a 0. Okay, this is a quadratic. And remember that to make a quadratic, right, if it has zeros, I can factor it. So I'm sort of starting with x squared, but the idea is I could factor this thing, and I don't know what the heck this factors into. I could pick some numbers so I would know what it factors into, but let's just look at, if I take something like x plus 1 and times x minus 1, then oh, I turned that off, didn't I? I was thinking, why can't I see that? Turn it off. Okay. So, right, then we have our zeros here from those factors. And so when I made that quadratic, right, if it factors, well, it has to look like this. It has to have, a 0 somewhere like that and somewhere like that. Okay, but those are the only two zeros it could have. So the problem is that, think about our manipulations of functions. If I had a quadratic that came down here and wiggled up and came down, you would say, well, it still only has two zeros, right? It wiggles like that. It still only has two zeros. However, if I just made a bigger, right, or a0 bigger, what does that do? It raises it up. And so if I had wiggles down here like that, at some point, maybe it would be there, those wiggles would have had to cross that x-axis a total of 4 times. Well, that can't happen. It's a quadratic, right? I mean, if it's factoring into 2 things and only 2 things. It can't be 4 things. If it factors into 4 things, oh, that's a quartic or a 4th degree polynomial. So that's where we get the idea of the wiggles. And I know that's very technical, but what we have is that you're only going to have as many possible troughs and peaks as one less than your zeros, right? Because every time I hit 0, okay, I hit 0, well, I have to, if I'm going to have a trough or a peak, so in these cases, these are both troughs, if I'm going to have a 0 and then have a trough, it has to come back, and so I'd have 2 zeros. Oh, only one trough. And so when we go to a cubic, then we'll make this not 0. There's a nice one, a cubic. And we'll go back here again and move me around. Woo! It's like a roller coaster. Okay, move me back down. Now you see, okay, this particular cubic, it happened to have 3 zeros. And so, and I'll just write it here, we won't graph it, but that would be something like, x, plus 2. Okay, there are 3 zeros. When I multiply those together, I get a cubic. Well, it can't be any bigger than a cubic. So if I have a cubic, at most it could have these 3 zeros, but see what happens then is I can only have 2 total peaks and troughs. Okay, only 2 total. And so I can keep that in mind as I look at things. Now, notice this one, it has 3 zeros, right? I can give it fewer zeros simply by increasing the A0 here and lifting it up. Now it only has 1 0. But it still has a peak and a trough, but that's the most it could have, and the reason that's the most it could have is if it has that, I lower it down until they cross 3 times, and that is the most zeros I could have on a polynomial of degree 3. So I can only have 2 of these changes in direction. That's another way to look at it, is it was coming down, it went up, it goes down, so this has to be at least a cubic. Now, it could be a 5th degree polynomial, or a 7th degree polynomial, or a 9th degree polynomial, because you could have irreducible things in here. So for instance, if this had been x squared plus 1, and then forget about the x minus 1, now that function will only have 1 0, because this part, you see, is never 0. And so it will only have 1 0. That will be a case where it will be a cubic, and it will have a slight wiggle to it, but it will not have the actual trough and peak. And so if I click that to show it, oh, well, see there, I proved myself wrong. It is showing a trough and a peak. Well, that's, I guess, yeah, sure, that's possible. But notice it only has the 1 0. And again, the A, B, C, D thing of trying to lower this, notice that if I make this 2 smaller, so a 1, see, as I made it smaller, so I was trying to lower this curve to make those humps like this go through there. They disappeared. And so if I have x squared plus 1 times x plus 1, then I definitely don't see the actual peaks and troughs. But I guess, sure, I can get those even with an irreducible polynomial here. We'll see more of that when we're doing our calculus and looking at slopes and that sort of thing. And you'll be able to, you can bring that back up with me and say, hey, you remember how you were wrong? And sure, I'll be wrong more than once. But again, hopefully either you figure out that I'm wrong or I figure out that I'm wrong and we correct it. But yeah, so at any rate though, we are not going to get more than 5 humps. And the problem is, if you're really listening to this, then my argument back here as to why 5 humps? I don't know why I said 5. Any more than the 2 humps, either an actual bump up or a bump down. So we aren't going to get more than 2 of these, but actually you can, if you go back to the argument I was using, I was saying, well, okay, if I have this and I try to lower it, right, it will eventually cross here. Well, yeah, I can lower it, but not simply by doing the 2. I change the problem and it won't be an irreducible polynomial anymore. So again, let me show that. So I have to write this as like a g of x. And now if here I do g of x minus 2, then you see I have the 0 there and the 0 there. But you see it was this whole thing, and then I did a minus 2 out here, which if I was going to factor it, well, I would have to multiply this all out, subtract the 2, and then factor that. Okay, so you know what I said about if you have these humps up here like this, then you could lower the function. Well, you can. I just did it here, and it now has you know, a 0 here and a 0 there, and one of these this 0 I think is a double 0. In other words, that's also a little relative maximum point. The function never goes over that. If I lifted it up just a hair, so I did like minus 1.9, now I see more of these little dots, and you know, so I could kind of lift it up, and I'm not sure why it's not showing the 0 there, but at minus 1.28 and 0, and then here at that 0, and there at that 0. So if I pick the right number, it's got 3 zeros. It looks like if I picked a 2, it had just 2 zeros, so it can have that. One's a repeated 0 if you factored it. This would be like x plus 2 quantity squared. And oh, and 0, 0. So interesting. But you know, so it's I think what that means, this is a bit of a tangent, but hey, you know, we're friends here, we can do this sort of thing. It looks like when I subtract 2 off of this, it ends up factoring as x times x plus 2 squared. Nope. Oh wait, that's not 2, that's why. X plus 1 squared, there we go. And so if I did a minus 2 out here, you see it factors into this, and so I do have my 3 zeros. Okay, it's not the same as that anymore. All right, so that's polynomials, and I think we'll stop it there. That's getting very long, I think, but looking at polynomials, you're looking at the wiggles, and there could be as many as these n minus 1. If n is the degree, then there could be as many as n minus 1 of these bumps and troughs, and then you just look at that if that's odd or even. If it's odd, then it's going to do something like this, either go back and forth this way or back and forth that way, up and down like y equal x. And if it's even, it'll be more like a parabola in that both ends will go up or both ends will go down. Okay, so that was linear and quadratic families of functions.